So far we talked about symmetric and asymmetric cryptography, and one of the big problems in using either of them is that you need to have keys, right? Obviously, others should not be able to guess these keys, because if they can guess, then they can break cryptography. So the question is, how do you generate these keys? Okay, and that's where random numbers come in. Okay, so random numbers are used to generate secret keys for bulk data encryption, right? Like what we talked about in the last topic. And these keys that are generated for in this manner are often called session keys, because typically what happens is that you use a public key based step to establish a session where each side of the connection is authenticated to each other and so on. And at that point, they establish a session key, and for the session key, you need a good random number generator. Similarly, if you're using RSA key or some other type of key, then once again you need to figure out what is you need to generate a key, and again the best way to generate a key is a random number generator, because how else can you generate something that others may not be able to guess, right? Because anytime you use a deterministic way to generate a key, somebody else can figure out exactly how that is done. So what you need to do is to have a non-deterministic way, or rather a random process to generate these keys, right? So the important thing to remember here is that we are not talking about statistically random looking numbers. We need true unpredictability, right? So most of you are probably aware of pseudo-random generators that we often use in statistics and analysis, and more importantly in a lot of simulations and in our programs very often. And these are generated actually in a deterministic way, right? One of the most common random number generators is what is called a linear congruential method, which simply takes a previous number, multiplies it by a constant a, and then adds some value, another constant, and then simply computes a modulo with respect to some base. And because of the properties of modulo, if you choose m appropriately, you can make sure that xn plus 1 and xn look as if they have no connection, right? So xn plus 1 looks random as compared to xn, but it's obviously not truly random, because anybody who knows xn can easily generate xn plus 1, right? Because these numbers a and x are fairly easy to figure out, and so it's not really, once someone knows what is xn, it's very easy to figure out what is xn plus 1, right? And even if you don't know what is a and x, if you see xn, xn plus 1, and xn plus 2, and xn plus 3, we're looking at four successive random number generators, or three successive random number generators. Three successive random numbers, you can figure out what this a and x are, and therefore really there is no use these types of random number generators for cryptography. Okay. So so what you end up doing is you need to rely on what are called true sources of randomness. Okay. Often radiation counters and radio noise are thought of as true sources of randomness, because cosmic rays and other things, other natural phenomena are thought to be truly unpredictable, and so they are natural sources of true randomness. But these are very difficult to obtain, so we need to come up with something that is easier to obtain in the context of our computers. And two such quantities are keystroke intervals and network packet arrival characteristics. And you might say, well, if I type, don't I type at a certain speed? Is it not predictable? Of course it's predictable, but what you should be looking at is the, you should measure the keystroke times, say at the level of nanoseconds. and then you look at the last, the 1,000 nanoseconds. So you just drop the more significant bits in the in terms of when you type the keys. And if you look at just say the nanosecond part of it, then you will see okay there is a lot more variability, and no human being, it's easy to believe that no human being can predictably type at the nanosecond level, right? So it's if you look at the nanosecond level, the intervals are just going to look like random numbers. And the same thing happens at the network packet arrival also. So if you look at what is the average rate of packet arrival, that may be predictable, but if you look at again the nanosecond or even finer granularity, then you're going to see that the inter packet arrival time is just so variable, right? And that's what we use for generating true random number generators. And most of today's operating systems have mechanisms that monitor these sources of randomness and use that to build what is called an entropy pool from which it can generate true random numbers, and which can then be used for key generation and so on. Okay, but these are sources of randomness, so doesn't really help. For instance, if you want to generate RSA keys, then you need to generate random numbers with certain properties. For instance, in RSA, you need to generate very large prime numbers. So how do you do that? The problem is that if you have a very large prime number, like say 1,000-bit number, how do you even figure out that it is prime? Because the typical way you can think of for doing checking whether a number is prime involves trying to divide it by all the prime numbers less than that prime number, right? You can be a little bit clever and then say, well, I only need to go up to square root of that number, and if I check whether it is divisible by all the prime numbers below the square root of that number, that's enough. But if you have a 1,000-bit number, then the square root of 1,000-bit number is a 500-bit number. And so if you have to enumerate all the prime numbers that are less than 2 to the power 500, well, you know that that's not something that's going to end before the universe ends. And so you can't really do the basic algorithm that you know for checking whether a number is prime is not going to work, and so that's why you need better techniques. And in particular, we rely on what are called probabilistic algorithms. So these algorithms don't tell you for sure that something is prime or not, but they can tell you that something is prime with a very high probability. Okay, and again, I'm not going to go through the specifics of how this is done. The more important point is to understand the concept that even though these numbers are big, there are techniques, probabilistic techniques, for checking whether the number is prime or not. And and this is Miller-Rabi test is one such technique where you run a certain test many times, and if you run the test t times, then the probability that it is a prime number is 1 minus 0.25 raised to the power t, which means that if you set t to be something like 1,000, right, then this probability is so high, right, and your expected failure rate might be once in many universe lifetimes, right? So that again, the probability gets so close to 1 that it's no longer necessary to worry about whether it is really prime or not. Okay, let's stop here.